Have you ever thought about just how intricate a 3D medical scan really is?
Oh, yeah, for sure.
It's like looking at a whole city, but it's made of with all these complex biological structures.
Yeah.
And the thing is, we're asking computers not only to see these images, but to actually understand them,
Right.
to be able to pick out these tiny anomalies that could be really important.
Yeah.
And to do that, it takes an incredible amount of computing power.
It's a huge challenge in the field.
Right.
Taking these just massive 3D data sets and then being able to actually get clinically relevant information from them.
Yeah.
Like, say you want to precisely outline a tumor,
Right.
that takes some really sophisticated tools and a lot of computational power.
Yeah, that makes sense. It's like one of the big bottlenecks we have in modern medicine.
Absolutely.
And that's actually what we're going to be diving into today. We've been looking at some research on this.
Okay.
And specifically, there's this paper called SegMamba, Long-Range Sequential Modeling Mamba for 3D Medical Image Segmentation. So it's this new model, SegMamba.
SegMamba.
And it's designed to try to understand these really widespread relationships within these incredibly detailed 3D medical images.
Right.
So it's about how can we get the AI to see the whole picture,
Exactly.
to understand the context of the entire scan and do it efficiently.
Right, because you need the whole context
Right.
to make a good diagnosis.
Yeah, the more information the model has,
Yeah.
the better it can be at identifying and segmenting these specific areas.
Yeah, and especially think about if you're trying to find like a small irregularity
Right.
within a whole organ.
Yeah.
The AI needs to be able to see how that small area relates to the whole structure to say, oh, this is actually an irregularity.
Totally. Now, we've relied on some, kind of standard approaches for a while.
Right.
Things like convolutional neural networks, CNNs, which are great at finding those little details.
CNNs have been the workhorse of medical imaging for a while now.
Right.
And they do a great job, but they have some limitations. So, architectures like 3D UXNet use large convolution kernels.
Okay.
And in the paper, they were talking about like a 7 by 7 by 7 size kernel,
Okay.
which helps to expand the receptive field.
Right.
So how much the network can see at once.
Okay, so maybe we should define receptive field real quick.
Yeah.
Because, for listeners who aren't as familiar,
Sure.
it's basically the area that the model can see when it's making a decision about a pixel, right?
Yeah, it's like the neighborhood around the pixel that the model is looking at.
Exactly.
So a larger receptive field lets the CNN consider a wider area.
Yeah.
But because of how convolutions work by design, they're kind of looking at small local areas.
Right.
They still really struggle to understand these long-range connections that are happening across a whole 3D volume.
Yeah. It's like trying to understand a symphony, but you can only hear a couple notes at once.
Exactly.
You miss the whole harmony
Yeah.
and the way the different parts relate to each other.
Right.
But then Transformers came along.
Yeah.
And they kind of changed things up, especially when it comes to understanding context.
Yeah.
We've seen this in natural language processing.
Yeah, like the large language models that everyone's talking about now.
Right.
Those are based on transformers.
Right.
And they're so good at being able to see the whole picture and understanding how different parts of a sentence or even a paragraph relate to each other.
Exactly.
That's because of their self-attention mechanism.
Okay, yeah. So how do transformers and self-attention kind of solve this global understanding problem?
Okay, so self-attention lets the model look at all the different parts of an image and figure out which parts are important to pay attention to when it's trying to understand a particular part.
Okay.
So it can weigh the importance of different parts of the image relative to each other,
Right.
no matter how far apart they are.
Yeah.
So it's like the model has this global view of the image,
Gotcha.
and it can use that to make better decisions. Now we've seen models like UNetter and SegMamba, which have brought that transformer power into the medical image segmentation world.
Right.
And they've shown some impressive improvements.
Yeah, they did really well.
Yeah, they've achieved significant improvements over the CNN-based models.
Okay.
However, this powerful ability comes with a cost,
Okay.
a big cost,
Okay.
and it's a computational cost.
Right.
So the self-attention mechanism in transformers has what's called quadratic complexity.
Okay.
Think of it like this. Imagine you're trying to connect every single point in a room to every other point in the room.
Okay.
The number of connections you need grows incredibly fast as the room gets bigger.
Right.
That's kind of what's happening with self-attention.
Yeah.
The computational demands explode as you start dealing with larger and larger images.
So that's a big problem when you have these massive 3D medical images.
It's a huge problem.
Right. So it seems like we have this trade-off
Yeah.
where CNNs, they're efficient,
Right.
but they don't always see the whole picture.
Whereas transformers can understand that global context,
Right.
but they need a ton of computing power.
Right. And that can be really limiting.
Yeah, for sure.
Especially in a clinical setting.
So this new SegMamba research introduces Mamba as kind of a potential solution to this.
Yeah.
So can you tell me a little about Mamba itself?
Yeah, so Mamba is this newer type of model called a state space model, or SSM.
Okay.
And it's shown a lot of promise in natural language processing.
Okay.
Because it can efficiently handle these long sequences of data while being much faster and needing less memory than transformers.
Okay.
So it's kind of the best of both worlds.
That's pretty exciting.
Yeah.
And we've seen some initial work trying to use Mamba in medical imaging.
Right.
I think in the paper they mentioned UMamba and VisionMamba.
Yeah, those were some earlier studies.
Right.
That were looking at how to apply Mamba to medical image analysis.
Yeah.
Mamba was kind of focused on these general medical image segmentation tasks.
And then VisionMamba was looking at using Mamba for understanding visual context more broadly.
Gotcha.
So kind of like taking a step back and looking at the bigger picture.
Right.
But the researchers behind SegMamba, they highlight that no one has really taken Mamba and specifically tailored it for the demands of 3D medical image segmentation.
Okay.
Which is a much more challenging task.
Right.
And that's really the core of their innovation here.
Yeah.
They're taking Mamba and they're saying, how can we make this work really well for 3D medical images?
Yeah, so how do they actually pull that off?
Okay, so SegMamba is a brand new framework.
Okay.
They're taking that U-shaped architecture, which is really common in medical image segmentation.
Yeah.
And they're integrating the Mamba model into it.
Okay.
They explicitly state that they think this is the first method to do this.
For 3D medical image segmentation.
Yeah.
Okay, cool. So let's get into how it actually works.
Okay, so the key to SegMamba is what they call the Tri-Orientated Spatial Mamba, or TS-Mamba block.
Okay.
This block is what allows them to capture those global features efficiently, but also maintain the multi-scale details that are really important for good segmentation.
Right, so when you say multi-scale features, you mean it can kind of see the forest for the trees.
Exactly. It can analyze the information at different levels of detail without needing to shrink the image down too early on.
Okay.
Which is something that some transformer-based methods like UNetter do, and that can actually hurt their ability to really capture all the multi-scale features.
Interesting. So what are the main parts of the TS-Mamba block?
So the TS-Mamba block has two main components.
Okay.
The first is the Gated Spatial Convolution Module, or GSC.
Okay.
Now, the researchers realized that a standard Mamba layer takes 3D data and flattens it into a 1D sequence.
Okay.
This is a really efficient way to process it, but you inevitably lose some of that spatial information that was in the 3D structure.
Right, it's like scrambling up a book.
Yeah, exactly.
You lose the arrangement of the words.
Right, so you need a way to keep that spatial context. Yeah.
Before you flatten the data.
Okay, so that's what GSC is for.
Exactly.
How does it do that?
So it uses two parallel pathways of convolution.
Okay.
The first pathway uses a 3x3x3 kernel, which is looking at what's happening right around a specific point.
So local information?
Local spatial information, yeah.
Okay.
And then the second pathway uses a 1x1x1 kernel.
Okay.
And this is more looking at different feature channels at a single location.
Oh, gotcha.
And then they take the outputs of those two convolutions and they multiply them together.
Okay.
This acts as a gate.
Okay.
It allows the model to decide which spatial information is actually important to pass on.
Interesting.
And then they take that gated result and they put it through another convolution and finally combine it with the original input using a residual connection.
Okay.
If you look at figure 2A in the paper, it gives you a good visual of this.
Okay.
But essentially what they're doing is they're using these two types of convolutions.
Right.
One looking at local areas, the other looking at individual features.
Yeah. And they're combining them in a way that lets the model decide which information is most important.
Before it even goes to the Mamba part.
Exactly.
Okay, so they're making sure they don't lose that key spatial information.
Right.
When they flatten it for the Mamba layer.
Exactly.
Okay, and what's the second part of the TS-Mamba block?
Okay, so the second part is the Tri-Orientated Mamba, or the TOM module.
Okay.
Now, the researchers also realized that the original Mamba model processes sequences in only one direction.
Okay.
Which is fine for text.
Great.
You read text from left to right.
Yeah.
But 3D medical images, they have relationships in all three dimensions.
Right.
You can move along the x-axis, the y-axis, and the z-axis.
Right, you could have a tumor growing in any direction.
Exactly.
It's not just left to right.
Right.
Okay.
So to handle this, the TOM module processes dependencies from three different directions.
Okay.
It takes that 3D input and turns it into 3 separate 1D sequences.
Okay.
One going forward through the volume, one going backward, and one going through the different slices of the scan.
Okay.
And then each of those sequences is processed by a standard Mamba layer.
Okay.
And then the results from all 3 directions are combined.
Okay.
To give that comprehensive understanding of the global dependencies.
So you're getting the whole picture from all angles.
Exactly.
Very cool.
And figure 2B in the paper illustrates that.
Okay, cool.
Mm-mm.
So they've got this GSC to hold onto the spatial detail.
Right.
And then the TOMOM to look at those relationships from multiple directions.
Right.
So the TS Mamba block is a pretty innovative way to get efficiency and comprehensive understanding.
It is.
But they don't stop there.
No, they don't stop there.
They have another trick up their sleeve.
They do. They also include what they call the Feature Level Uncertainty Estimation Module, or FUE.
Okay.
And uncertainty estimation, I mean, it makes sense in medical imaging.
Totally.
You want to be as confident as possible in the AI's analysis. So when you're looking at those multi-scale features coming from the earlier parts of the network,
Okay.
there's naturally going to be some uncertainty
Right.
about what's in the image. Yeah. Is this the background?
Right.
Is this healthy tissue?
Yeah.
Is this a problem area?
Exactly.
So the FUE module aims to amplify the features that have lower uncertainty across the different scales.
Gotcha.
And it does this in the connections that skip across the U-shaped architecture.
Right. So those skip connections are allowing the network to reuse information from earlier stages.
Right.
So how does FUE help with that?
Okay. So it calculates an uncertainty score for
Okay.
each feature map at each scale.
Gotcha.
It's basically looking at the average value across all the different feature channels.
Okay.
And then uses a mathematical function called a sigmoid.
Right.
To kind of squish that value into an uncertainty score.
Okay.
Between 0 and 1.
Okay.
And they call that U for uncertainty. And then the final enhanced feature is calculated by taking the original feature and adding to it the original feature multiplied by 1 minus the uncertainty score.
Okay.
So if a feature has low uncertainty,
Right.
meaning U is close to 0, it gets a bigger boost.
Gotcha.
And this helps the network prioritize the more reliable information.
That makes sense.
And you can see that calculation in equation 4 in the paper.
Okay, so they're really trying to make sure that the network is focusing on the most trustworthy information.
Exactly. They want to make sure the model is paying attention to the right things.
Yeah, so to test out this model,
Right.
they didn't just use existing data, they created a whole new data set.
They did.
And it seems like they specifically focused on colorectal cancer.
They did.
So why colorectal cancer?
So colorectal cancer, or CRC, is one of the most prevalent and serious types of cancer worldwide.
Wow.
And it's really important to have good diagnostic tools to catch it early.
For sure.
But the problem is that the existing data sets for 3D CRC segmentation were kind of limited. Okay.
They were small, and a lot of them weren't publicly available.
So they created their own data set to address that?
Yeah, they created CRC 500.
Okay, so what can you tell me about CRC 500?
So it's a pretty large data set.
Okay.
It has 500 3D CT scans.
Okay.
And each scan has been really carefully annotated by expert radiologists to mark the colorectal cancer regions.
And these scans were collected over a long period of time?
They were, yeah.
Okay.
From January 2008 to April 2020.
Okay.
And of course, they've removed all the identifying information.
Of course, right.
But what's really important is that each scan was first annotated by one expert doctor, and then those annotations were checked and refined by a second expert.
So it's double-checked?
It's double-checked.
Okay, so you have 2 sets of expert eyes making sure that the annotations are correct.
Exactly.
That's really important for making sure the data set is accurate.
It's crucial.
What about the technical details of the scans themselves? Okay, so all the CT scans have a resolution of 512 by 512 pixels.
Okay.
But the number of slices along the z-axis, that varies.
Okay.
From 94 to 238.
Right.
With a median of 166.
Okay.
And the spacing between the pixels and the slices, that also varies a little bit.
Okay.
But if you want to see some examples from the data set, you can look at figure 3 in the paper.
Okay, cool. So it sounds like a really substantial and well-annotated data set.
It is.
So for the experiments, they tested SegMamba on this new data set.
They did.
And also some existing public benchmarks.
Right.
Which ones did they use?
They used CRC 500, of course.
Right.
And they also tested it on BRATS 2023.
Okay.
which is a data set for brain tumor segmentation
Okay.
from MRI scans,
Gotcha.
and then AIIB 2023,
Okay.
which is for segmenting the airway tree.
Okay.
So 3 very different types of segmentation tasks
What?
to show how well this generalizes.
That's cool.
So for BRATS 2023, the goal is to segment different parts of brain tumors. So the whole tumor,
Okay.
the enhancing tumor and the tumor core.
Gotcha.
And then for AIIB 2023,
Right.
the task is to segment the entire airway tree
Okay.
with all of its branches.
Gotcha.
So they want to see how well the model can delineate these different structures.
Yeah. And how did the model do on the BRATS 2023 data set?
Okay, so looking at table 2 in the paper,
Okay.
SegMamba achieved the highest DICE scores and the lowest HD95 scores for all 3 of those segmentation targets.
Wow.
So that's the whole tumor, the enhancing tumor and the tumor core.
Okay.
And it outperformed a whole bunch of other methods.
Okay.
They tested it against CNN-based approaches like SegResNet, UXNet, MedNext,
Okay.
and transformer-based methods like UNetter, SwenUnetter, and even SwenUnetter v2.
Okay.
So it was really a comprehensive comparison.
And just as a reminder for people who may not be super familiar with these metrics,
Yeah,
a higher DICE score means that there's better overlap
right.
between what the AI segmented and the ground truth. And then a lower HD95 score means that the boundary detection is more accurate and robust.
Right.
So it's basically saying that it's better at outlining those tumor boundaries.
Right, so it's really good at finding the tumors.
Yeah.
And it's really good at precisely outlining them.
That's really promising, especially for something like brain tumor segmentation,
Absolutely.
where it's really important to know those exact boundaries for treatment.
Exactly.
Okay, so really strong results there.
Yeah.
What about the AIIB 2023 for segmenting the airways?
Okay, so for AIIB 2023,
Okay.
which is also in Table 2,
Okay.
SegMamba achieved the top scores in IOU,
Ooh.
DLR,
Okay.
and DBR.
Okay.
These are all metrics that are really important for segmenting these continuous branching structures,
Right.
like the airways.
Yeah.
And it suggests that SegMamba is really good at capturing that whole airway tree.
The whole structure.
The whole structure, including all those tiny branches.
Very cool.
Yeah.
And what about their newly created CRC 500 data set?
So on CRC 500,
Okay.
which you can see in Table 3,
Okay.
SegMamba once again achieved the best DICE score
Okay.
and the lowest HD95 score.
Nice.
And the researchers point out that in this data set, the cancerous regions can be very small
Okay.
and subtle.
Right.
So the fact that SegMamba can detect them is really significant.
Yeah, especially for early diagnosis.
Exactly.
Now, I know that the paper also includes some visual comparisons
They do.
in Figure 4.
Right.
What did those show?
Those visual results really back up those quantitative findings
Okay.
across all 3 data sets.
Yeah.
SegMamba consistently shows that it can accurately find the boundaries of the structures being segmented.
Right.
And it shows better consistency compared to other methods.
So it's not just better based on the numbers, but it's also visually better and more reliable.
Exactly.
That's really great.
Yeah, it's what you want to see. You want a model that's not just doing well in the numbers, but is actually producing results that you can trust when you look at them.
Yeah, absolutely.
And that's what they're showing here.
So to really see which parts of the model are contributing the most,
Right.
they did what's called an ablation study, right?
Right. An ablation study is where you remove different parts of the model
Okay.
to see how that affects the performance.
Okay.
So you can figure out which parts are really important.
Gotcha.
So they did that in Table 4.
Okay.
They systematically removed or added different components of SegMamba,
Okay.
and they tested it on the CRC 500 dataset.
Gotcha.
So they started with a basic Mamba model, which they labeled M1,
Okay.
and then they progressively added the GSC module.
Okay.
That was M2.
Gotcha.
Then they added the TOM module.
Okay.
That was M3.
Okay.
Then they added both GSC and TOM together.
Gotcha.
That was M4.
Right.
And then finally, they added the FUE module to get the complete SegMamba. So they're kind of building it up piece by piece to see how each component contributes.
Yeah. So what were the key insights that they got from that?
Okay, so the results showed pretty clearly that adding the GSC module improved both the DICE and HD95 scores.
Compared to just the basic Mamba.
Right, compared to just that basic Mamba model.
So it shows that capturing those spatial relationships early on is really important.
It's really important.
Yeah.
And then adding the TOM module led to further improvements.
Right, because you're getting that multi-directional information.
Exactly. It allows the model to learn global information from multiple directions.
Yeah.
And then combining GSC and TOM together resulted in even better performance.
Okay.
And then the full SegMamba with the FUE module achieved the best results overall.
So each component is adding something to the model's success.
Exactly. Every piece of the puzzle is important.
Now, the paper also talks about the efficiency of SegMamba,
Right.
especially when compared to those transformer-based methods that are computationally expensive.
Yeah, because that's a big concern, right? If you have a model that's super accurate,
Right.
but it takes forever to run, or you need a supercomputer to run it,
Yeah.
it's not going to be very useful in a clinical setting.
Right.
So they compared SegMamba's memory usage during training and its inference time to a bunch of other methods.
Okay.
So they looked at methods that use large convolution kernels like UXNet,
Right.
and then SWIN transformers like SwenUnitter,
Right.
and they even tried a direct implementation using just self-attention.
Okay.
And interestingly, that self-attention-based method actually ran out of memory during the experiments,
Wow.
which really highlights just how computationally demanding those models can be.
Yeah, that's a huge problem.
Yeah.
So how did SegMamba do?
So SegMamba, with its TS-Mamba module, it required less memory during training,
Okay.
and it had faster inference times compared to those other methods.
Okay.
Even when it was processing these really long sequences of data. They tested it with sequences up to about 260,000 elements.
Okay.
So that's a lot of data to process.
Yeah, for sure.
But SegMamba was able to handle it efficiently.
So it's able to get that long-range dependency information,
Right.
but without the huge computational cost of transformers.
Exactly.
So to sum it all up, what are the main takeaways from this SegMamba research?
Well, this work really establishes SegMamba as the first general 3D medical image segmentation method using that Mamba architecture.
Okay.
And its big advantages are that it can effectively model long-range dependencies
Yeah.
in that volumetric data.
Right.
And it has really high inference efficiency.
Okay.
And they showed this across different medical imaging tasks.
Right.
And on that new large-scale CRC 500 dataset that they created.
So they really put it through its paces.
They did.
Yeah.
And it passed with flying colors.
Awesome.
Yeah.
And speaking of CRC 500,
Right.
that seems like a major contribution in itself,
Yeah, I think that data set is going to be a really valuable resource for the community.
especially for research into colorectal cancer.
Exactly.
So when we think about the future of medical image analysis,
Right.
this research on SegMamba really makes you think about the potential of these efficient long-range modeling techniques like Mamba
Yeah,
to revolutionize how we analyze these images.
absolutely.
I mean, could this be a big step towards developing even faster, more accurate diagnostic tools?
Yeah, I think it has the potential to be a real game changer.
Right, that can handle those complex 3D scans
Right.
without being limited by computational power,
Yeah,
which is a huge problem right now.
it is.
It's really exciting to think about the possibilities this opens up
Yeah, definitely.
for improving patient care.
Absolutely.
And I'm curious, for the listeners out there, do you think that these types of efficient models are going to be the key to unlocking even more powerful AI tools for healthcare?
It's definitely an area to keep an eye on.